So we have heard about some great things about very formal things, and now I would like to draw your attention to one application scenario. So what's this talk about? This talk is about generating trustworthy board management controller based on SEL4. And as a part of that, we need to generate trustworthy I2C drivers. And this talk is about our progress doing it. So what is this board management controller and I2C? Well, let's take a look at this typical dual socket server. There's CPUs, DRAMs, Ethernet, and a few more things. And this is we, as a users usually care about. But actually, behind the scene, there's a pretty large pieces missing here. So in every modern server, there's a board management controller, or BMC, that is responsible for clock generation, voltage control and monitoring, and temperature and fan control. If your BMC is corrupted, nothing will work. Or worse, your hardware will be a dumpster fire. So by extension, not only servers, every mobile device also has an BMC. Essentially, it means every computer in this room have one BMC. And all these functionalities shown here are controlled over I2C, inter-integrated socket, or I2C, IIC. It's a low-level communication protocols, and it's actually everywhere. It's also in your DRAM and Ethernet. Oh, by the way, speaking of Ethernet, your BMC also have an Ethernet because people want this server to be remotely manageable. Well, I guess that's a pretty large attack surface. And yes, this is the critical piece that manages your server behind the scene and how it is built nowadays. Well, the state-of-the-art BMC firmware implementation is OpenBMC, a Linux distribution. There are management scripts written in Bash, in Python, sometimes Python 2. There are programs written in C, and programs communicate over dbus. And there's even a web server in your BMC because it is attached to the internet. And at this point, you should be very afraid. This is the piece that manages your server. And here is SEL4 Summit. And this is the critical pieces that SEL4 should be used to secure. So we apply a now pretty well-known approach, cyber-retrofit, to secure BMC. We use SEL4 as the kernel and run the Linux and OpenBMC in a VM. And we extract the critical pieces like power management out into SEL4 and retrofit it as a highly assured component. But there we have a problem. We have SEL4 as kernel, it's very secure, very high performance, but now we need to write our own drivers. And specifically, we are interested in the I2C stack here. How are we going to write trustworthy I2C stack? And before diving into our approach, here's a bit more background on I2C and why it is different. Well, I2C is a bus-based protocol. It has two wires, a clock, SCL, and a data, SDA. There's one control, on an I2C bus, there's one controller and one or more responder. In BMC, the controller is the BMC itself, and the responder are those power regulator, temperature sensor, and so on. It is always the controller that drives the clock line with some exception. And depending on the transaction type, either the controller or the responder drive the data line. So on those two wires, the electrical signal encodes these four symbols. And I2C is also the layered protocol. So from top to bottom, the drivers will issue read and write transactions, which are broken down into bytes, which are further broken down into symbols on the bus. And here, the electrical level is more like a placeholder. In actual drivers, is an interface that actually drive the two wires. For example, maybe a big binding drivers in software. And one way to model the I2C stack is to consider every layers as a coroutine. So here we are dealing with discrete ticks inside the stack, but assume that there will be an properly function tickers at the electrical level, layer to convert those ticks to the actual bus ticks. So let's focus on the interaction of the lowest three layers. So for example, if the byte layer wants to send a star symbol, it first communicates with the symbol coroutines. And then the symbol coroutine will say, let's set both SCL and SDA to high. And then it reads back the voltage level from the wires. And then it says, let's keep SCL high, but set SDA to low. And this sequence encodes the star symbol on the wires. And then the symbol layer finished its work. It talked back to the byte layer saying that everything is done. So far so good, but only if all the devices conform to the standards. There are actually many devices out there that have Quirks, which means part of the device does not conform to the standards. For example, here in the middle, we show the standard I2C read transaction. So the controller first supplies the target I2C address, which is in blue, and then a read bit indicating that this is a read transaction. And the following payload bytes are supplied by the responder in yellow because this is a read transaction. However, the AS5011 health sensor does it differently. The first payload byte, instead of being supplied by the responder, is actually supplied by the controller as the register index to read from. Essentially, it changed the meaning of the read bits. It no longer indicates this is a read transaction, but a read operation to the sensor's register. And this is a violation of the transaction abstraction. And here we are only showing one example. In practice, there are like other devices like this KS0127 video encoder that have Quirks. Your I2C controller on your Raspberry Pi also have Quirks. There are CVE records assigned to I2C issues. And in Linux, in the Linux source code, there's an array that records non-I2C Quirks. And as you can imagine, this is a problem for verification. How are we going to model and verify buggy hardware? And additionally, unlike other devices that has point-to-point connection with BMC, the nature of shared bus indicates that if one device fails, the system may just stop working because interference between those devices. And since we are building the trustworthy I2C stack for the BMC, we want to ensure that the system works, even if there are multiple devices interacting with each other. So this is how we solve the problem. We developed a framework called FOI, which means Ivy in German, that for generating efficient, verified, hybrid hardware-software drivers for I2C device. The high-level idea is to specify the device once, model check the whole system, and then generate drivers from it. So a key question here is, we get some property from the model checking, and how we ensure those properties are transferable to the actual driver code being generated. And this will be the main focus of this talk. And for many more details, you are very welcome to take a look at our paper that I'm going to post at the end. So the first step to use FOI is to specify the whole stack, not only the controller, but also the responder device. So here we adopt the top-down approach. First, we specify the layers and their interface in a very lightweight domain-specific language, ESI or FOI system information. So here on the left, we show an example that specifies the electrical layer and the symbol layer and the interface in between. So here in the interface definition, there are two arrows that just indicate the direction of the information flow, whether it's from electrical to symbol or the reverse. And after that, we can specify each layer as a coroutine, or informally, it's also a finite state machine that runs indefinitely. And there we use a subset C domain-specific language called ESM, or FOA state machine, to do that. So on the right, we show an example of the symbol layers. And here, I would like to draw your attention to those torque derivatives. These are basically coroutine switch. They are the way that one layer communicates with the other layers. Here, the switch will take the output, the value to be passed to the other layer, and pass the control to the other layer, and then get back the result, and then resume execution from that. And we model the stack in layers, and one important reason is that now we can reuse those layers to model all kinds of devices, including the non-compliant device. So recall that the AS5011 sensor, they violate the transaction abstraction, but actually the layer below transaction is unaffected. We can simply reuse those layers without modification, without the need to re-verify them, but only build specialized transaction and drivers layers on top. And with that, we can model as many devices as we need with minimum engineering effort. And once we have the whole system specified, we can model check it. And to do that, we need to translate ESM to Promula, the language for the spin model checker. So in ESM, layers are coroutines. This maps well to the process in Promula, which, as its name suggests, are process that runs concurrently. And process communicates through channels, and on the right, we show that the symbol process have two channels connected to the byte layer above of it, one input channel and one output channel. And it also has two channels that connected to the electrical layer, which is not shown here. And this channel carries the payload of the torque derivative. So for example, the torque operation here will translate to one write to the output channel, and then a read from the input channel. And here we use a Promula channel with zero buffer, so they are synchronous channels. So the message is passed when the other end waiting for receival. So basically, it's synchronous call, informally. And once we have the whole stack translated from Promula, we can start constructing verifiers. So there we still have some additional Promula code to be written. So here we show a unit on the test that is the byte layer and below for one controller and one responder configuration. And on the top, we need to write an input space specification, which says what input can byte layers get from above. And on the right, we have a behavior specification that describes what is the behavior of this unit on the test. For example, it would say, if the controller sends byte 42, the responder should also receive 42. And this is an example of the functional correctness assertion in the verifier. And this whole verifier is supplied to the spin model checker, which check there's no leaf lock, deadlock, and no functional assertion failures inside it. And a slightly more formally, if we trust that the input space specification captured all valid inputs from above, and we trust the Promula backend of FOA, then we can say the verifier pass means that the unit under test specified in ESI and ESM behave according to the I2C standard without leaf and deadlock. So by behaving according to the standard, it means the unit under test only generate the allowed trace that is encoded in Promula using its non-deterministic choice, and which specify all the allowed traces. So for example, here, if we, for the byte layer, it means the controller send a star symbol, and then both devices read it, and then one or more bytes are sent, and then stop. You cannot send bytes without a start or stop before a start. And further, if we additionally trust the C backend, which I'm going to cover soon, and trust the actual input and at runtime, plus trusting the code is correctly compiled and integrated, then the generated C code also preserves those properties. And before I dive into the C backend, we can start filling this table as a quick summary. So in layers are specified as coroutines in ESM, which maps to process in Promula. And interlayer communications, which are talk derivative in ESM, maps to channel operations in Promula. And when we actually generate driver code, we want conceptually equivalent implementation like this, so that we preserve, so that the property we get is transferable to the actual driver code. And to do that, we need some lightweight software implementation of coroutine. I mean, coroutine itself is a lightweight software implementation. Like if we are thinking of implementing them as process or thread, there would definitely be an overkill because those layers are all very lightweight. They are not computational heavy. But when we want to implement them as coroutines, we want to introduce minimum dependency, like we don't want inline assembly or dependency on any library. So we choose one specific implementation called case statement-based implementation. So here, the first step is to rewrite those layers into function in C. And then the talk derivative, some of them can be converted to direct function call. So let's say we take the left one, the talk symbol start, and transform it into a function call, into symbols with the start and the output pointers as arguments. But now on the opposite side, we cannot take that talk derivative as the function call as well, because otherwise the stack frame will only grow until overflow. We need to have a way to tear down the stack frame. And here's how we do it. So first, instead of making a function call, we actually write the output value to the output pointer, through the output pointer, and then make a record of the current position into this static variable pose. And then we return. And on the next entry of the symbol function, there's a big switch statement at the beginning that go back to the point after return and resume execution from that. And in this case, we have a way to switch to another layer, but instead tear down the stack frame for once. And there we have a nice implementation of coroutines without any dependency on any library. And just yesterday, I noticed that the microkit also introduced coroutine libraries, which was like 3 or 4 months ago that get published on GitHub, which is good. And maybe that will make this implementation more clean and elegant. And one good thing about this approach is that the function call and the return are actually interchangeable. So because we are generating practical driver code, we actually care about how this code gets integrated into the actual application. So here we borrow the idea of calling graph and implement something on it. So for example, at the left, if we have an application that wants a driver library, if the application wants to call into the topmost layer, we specify that layer as the calling point. And then the FOI compiler performs that first search on the graph and make all the forward edge as function call and the backward edge as return. In this way, we get a piece of code that nicely integrated into the application. The application can just directly call into the top layer, and the lowest layer will call into maybe some GPIO drivers that actually big bang the wires. And similarly, if we want a server process, maybe a server process on SEL4 as a component, that is get driven by a GPIO event loop from the lowest layer, we specify that layers as the calling point, and then the generated code will be seamlessly integratable into the whole system. And there are many more use cases of this system. And the good thing is that the specification actually don't care about this. All it cares is using the torque derivative. And the calling point can be specified at compile time using just parameters to the FOI compilers. And by the way, on the right, we also shows that we can actually generate a simulator for the whole I2C network in this way. So we have a infinite loop that call into both the controller stack and the responder stack, and they are connected to the scanf and printf, and there we get a simulator. And as a quick summary, for the C backend, it maps the coroutine in ESM into this case statement-based coroutine, and the torque derivative into coroutine switch. And also, FOI compiler has an HDL backend that generates some hardware description language that can be used to implement hardware drivers on reprogrammable hardware like FPGA. I don't have time to talk about it in detail here, but if you are interested, talk to me later after this talk. But I'm going to demo this. So here I get the actual BMC from Anzian, which is a server that we built at the system group at ETH. So this BMC is now plugged in on a different board, but it's exactly the same BMC that we use in production. It's a Zinc ultra-scale MPSoC, which has a CPU and an embedded FPGA. It is slightly more powerful than most BMC used nowadays, but arguably, industry start putting their customized silicon root of trust into their BMC. So we expect that hardware drivers will be useful in the future. And I'm going to give a very quick demo that runs hybrid software hardware drivers that split between the driver layers and the transaction layer. And here the BMC is connected to an EEPROM, which is basically a byte addressable flash that you can read from and write to. And on the BMC, we run SEL4 microkit. And I'm going to quickly show how the system is configured and shows that we can actually read from and write to the EEPROM if nothing breaks. So here, I will quickly show how the system is configured. So this is the system definition using microkit. So here we see a protection domain, which is the pretty standard serial server that multiplies the serial ports. And we have another protection domain, FOI, which is the software part of the drivers, plus a very simple console. And we have a memory region that interfaces with the hardware part of the driver that get maps into this software part. And we have an interrupt that interfaces with the hardware part. And we can take a look at this list of helper function that the generated driver call into. Those functions are handwritten, and they provide an interface to they provide the interface to interact with the hardware part through SEL4. And maybe we can take a look at this MMIO wait function, which is a helper function to wait for interrupt using SEL4 call, system call. So it waits for the interrupt and then acknowledge the interrupt so that acknowledge the interrupt, and after that you will use those pretty standard MMIO helper function to interact with the hardware part. And here is the generated drivers. So here we see how the code is rewritten automatically by the FY compiler. We see the switch statements and a lot of rewriting happening here, but this is all done automatically. And I will give a very quick demo on read and write this EEPROM. Oh. Right. So here I just restart the board. And then it first get into U-boot. And yes, for time limits, I have all the binary already compiled on the board. And it boots pretty quickly. And here we see this is SEL4 booting and into this microkit monitor, and then goes into our console. And first, let's try read from one address this 06 for maybe 1 byte. Yes, it gets some results and say everything is okay. And we write to the same address, maybe let's say 42. Is that okay? And then we read from it. It's 42. There we go. We have a very, yeah, thanks. All right, very shortly, I will give you a glimpse into the future of this work. So one direction is to extend the stack vertically. Now we have modeled the I2C stack, but maybe we can extend it to the protocol built on top, like assemblage or even the BMC logic. Another way is to implement more way to talk between layers. For example, we can maybe have a way to talk through I2C so that we can compartmentalize the stack further. And yet another way is to build stack for other protocols like SPI or CAN, which are also protocols for low-level management, and they are all layered protocols. So we think they are a very good fit into for FY. And yes, we have a paper that have many more technical details inside it. You are very welcome to take a look at it. And everything, the FY compiler, the model, and even the FPGA design are all open source. You can find it here. And I'm very happy to talk with you for your ideas, your thought on it, some maybe thought on other application, and talk to us later. And thanks. I'm happy to take questions.
Thank you, Zikai. And Courtney, are you ready to come up next? Where is our next speaker? Okay, so we'll take one question while we're swapping out computers. If there's one, Anna?
Hey, this looks really cool. I was wondering, so verification gives us a lot, but hardware also likes to throw sad things at us. How much have you thrown like tests, like fuzzing and extensive testing at it, and have you found anything not covered by your tools?
Do you mean like using like things like fuzzing to?
Yeah, any kind of stress testing, really. Have you found anything that like edge cases that?
We haven't. So far, like the verifiers are constructed manually, and we try to cover as much input space as possible. But of course, like all the model checking, we also encounter the scalability issue, which we have a lot of detail in the paper. And yes, but that's definitely a good idea, like maybe using some randomly generated input to try to stress test the stack. Yeah, that's definitely a good idea and maybe a future work. Yes, thanks.